Hello everyone, myself Roshni of registration number 18BEC0369. Now I'm going to present my COA digital assignment 1. Here we were asked to answer 10 questions, and for this we need to choose a microprocessing element such that we can answer all the 10 questions. So the microprocessing element that I choose is PIC16F627 or 628. And our first question is to draw the clear block diagram of the IP selected. This is the block diagram of my microcontroller, and for drawing this block diagram, the tool that I choose is draw.io. Draw.io is very easy and compatible to make block diagrams. It is also editable easily, and we can save in any format that we like. This is how I made the block diagram. And then we were asked to draw internal diagrams of each and every block. This is a pin diagram of PIC16F62X. Coming to the internal block diagrams, this is the timer diagram. This is a watchdog timer. This is the USART receiver block diagram. And our second question is to provide the instruction set for microprocessing element with details like clock cycle, memory required, flags affected, and types of instructions. Basically, there are two types, that is data processing operations and program sequence control operations. Data processing operations contains copy data between register, manipulate data in a single register, arithmetic operations and logic operations. And coming to the program sequence, unconditional jump, conditional jump, call and control. These are a few words that we often use, word list that we often use while giving the instructions. F, W, B, D, label, TOS, and the brackets. F is basically used to display the memory location in a microcontroller. W represents work register. B represents a bit position in F register. D represents a destination bit. Label gives the group of 8 characters which marks the beginning of a part of the program. TOS represents the top of stack, and the square brackets for options, and these brackets for bit position inside register. These are the few instructions on data transfer. And here are the instructions related to arithmetic and logic, and few instructions for bit operations, and these are for control operators, and some other instructions. I took the help of instruction set of my particular IC in order to answer this question. And the third question is to explain the microprocessing element architecture. Basically, the family of PIC can attribute a number of architectural features found in RISC architecture, RISC microprocessor. And here the specifically PIC16F62X uses a hardware architecture. In hardware architecture, program and data are accessed from separate memories using separate buses, which improves bandwidth. It allows instructions to be sized differently than 8-bit wide data world. A technique of two-stage pipeline is involved to fetch and execution of instructions. And this is the block diagram of PIC architecture. At the same .io tool is used here also. And coming to the fourth question, we need to correlate the microprocessing element architecture, which we have already discussed in further modules. Here we just discussed about hardware architecture. Now we will be correlating this with the microprocessing element that we have studied. As we just discussed, hardware architecture is a digital computer architecture whose design is basically developed to overcome a few drawbacks of von Neumann architecture. Von Neumann architecture, this is the block diagram of von Neumann architecture. The information of input device is sent to the central processing unit. Here the data is also transferred between central processing unit and memory unit, and then the output is sent. In hardware, all the 4 operations happen simultaneously, like the information between ALU and control unit and data memory, control unit and IO, similarly control unit and instruction memory. Everything happens simultaneously. And these are the terms with which I correlated. Memory location. Instructions and data can be stored in the same memory in von Neumann. Instructions and data are sorted separately in hardware. Pathway. Von Neumann follows the same pathway. Hardware follows a single pathway for instruction and data. Number of cycles. Clock cycles are required to execute single instruction. Single cycle is enough to execute an instruction in hardware. Buses, there is common bus for data and instruction transfer. Here, separate buses are used for transferring data and instruction. Functions of CPU. CPU can't access instructions and read or write at the same time. CPU access instructions and read or write at the same time. Von Neumann is cheaper in cost, whereas hardware is costlier when compared with von Neumann. Von Neumann is generally used in computers. Hardware is generally used in microcontrollers and signal processing. And the fifth question is to elaborate register organization of microprocessing element. Here are the addresses of the registers, and this is the name of the register, and this is the function of the register involved in the microprocessing element. And here are a few status registers. Status registers consist of 8 blocks. R represents the readable bit, W is writable bit, or W0. In the sense, this bit is readable as well as writable. U is unimplemented bit, read as 0. N is a value at POR reset. X is unknown at POR reset. And coming to option registers. These are the option registers. PS0, PS1, PS2, PSA. All these are read or write, as well as TOSC, TOCS. These are also read or write. And then intcon registers. Here everything is read or write. And coming to PIE1 register, PCON register, Sixth question is to explain the type of algorithms used for signed or unsigned calculations, and these are the two algorithms for addition. Syntax add LWK, and the other syntax is add WF F, D. Operation involved is when the contents of W register is added to a constant K, the result is stored back in the register W. Here the flags affected are C, DC and Z. And coming to the example, before instructions, the content saved in W is 0x10. When we use the instruction add LW 0x15, 15 constant is again added to this instruction, and hence after the instruction the content in the W register is 0x25. And similarly for syntax add WF F, D, here there are two possible storages of the result. When D is 0, the result is stored in W register, and if D is equal to 1, the result is stored in F register. Operation involved is when F register content is added to the contents of W, the result is stored in D. And coming to the subtraction now. Syntax is sub LWK. Here the operation involved is when the contents of W register is subtracted from constant K, result is stored back in the register W. And the same flags were affected here also, C, DC and Z. K is from 0 to 255. Before instruction, W is 0x01, carry is X and Z is also X. When we start the instruction sub LW 0x03, the content of 0x01 is subtracted with 0x03, and after the instruction carry becomes 1 and W is 0x02. Here this happens when the result is greater than 0. Similarly, when the result is 0, the carry is 1 and Z is also 1. When result is less than 0, the carry is 0 and Z is also 0. W is based on the result added, and by using the syntax sub WF F, D. Here the same as we discussed before in add WF F, D. If D is equal to 0, the result is stored in W register. If D is equal to 1, the result is stored in F register. The contents of W register is subtracted from the contents of F register and stored in D. The flags affected are C, DC and Z again. So when the result is greater than 0, the carry flag is 1, W is 2 and Z is 0. When the result is 0, register is 0, W is 2, C is 1 and Z is 1. When the result is less than 0, W is 2, C is equal to 0, Z is equal to 0. Now for multiplication. The syntax involved is and LWK and WF, F comma D. Operation that we use is W dot and dot K, and the result is stored in W register. Here the flag affected is only Z. And LWDX5F. So before instruction, W is 0x83, that is this in the hexa binary form. After instruction, the multiplication process is done and the result is 0x03. This will be stored back in W. And WF, F comma D. If D is equal to 0, the result is stored in W register. If D is equal to 1, the result is stored in F register. Similarly, the example. Flag affected is only Z. Now, 7th question is to find what type of control logic unit used and correlate its performance with the type of control unit in module 3 in our syllabus. A PIC microcontroller integrates all types of advanced ports and memory modules. Control unit used here is hardwired. This controller has feature to operate with high speed and it is also very flexible. Hardwired control unit involves a control logic to be implemented with flip-flops, gates, decoders and other digital circuits. Hardwired control consists of 2 decoders, 1 sequence counter and number of logic gates. Now we correlate between hardwired and microprogramming control unit. The approach involved in hardwired is security approach. Whereas in microprocessing element, the approach is through program. The mechanism involved in hardwired is it generates control signals to execute the instructions in a proper sequence. Whereas in microprocessing, each control signal differs from other depending on a bit pattern. Hardwired control is faster when compared in microprogrammed controller design. In hardwired, RISC instruction is followed, whereas in microprocessing, CISC instruction is followed. In hardware, the instructions works for only simple instructions, but microprogramming works well for control instructions also. The control memory is not required in hardwired, whereas control memory is required in microprogramming. Hardwired is more costlier. Microprogramming is cheaper than that required for hardwired. This is a block diagram of hardwired and this is the block diagram of microprogrammed control unit. Here for hardwired, all the instruction decoder instructions, external input instructions, conditional signal information, step counter information is all sent to the control signal generator, and from here the information is passed to hardwired control unit. Similarly, in the microprogramming, the instruction register is first passed to the microprogrammer address generator, from here to the control store and then to the control unit organization. Our 8th question is to explain the memory management system in the processing element selected and to list the addressing capabilities, memory mapping techniques followed, and then we need to find average of memory, advantage of memory design and management technique over the concepts given in module 4. PIC memory organization comprises of 2 different memory organization: program memory, data memory. Program memory. This has a 13-bit program counter capable of addressing 8K cross 14 program memory spaces. 8K address with 8K address program memory space, 14 elements. These are the 8 stack levels in the program memory, and then the interrupt vector and then the reset vector. Coming to the data memory. Data memory is mainly divided into 4 banks: bank 0, bank 1, bank 2, bank 3. When RP1 and RP0 both are 0, bank 0 is selected. The location for these registers are given here. When RP1 is 0 and RP0 is 1, bank 1 is selected. When RP1 is 1, RP0 is 0, bank 2 is selected. When both RP1 and RP0 are 1, bank 3 is selected. These were implemented as static RAM. Direct addressing and indirect addressing modes. Data memory, here are the 4 banks, 00 for bank 0, 01 bank 1, 10 bank 2, 11 for bank 3. Here we select the bank RP1, RP0, and then here we select the location. Similarly for FSO register, bank select and the bank location. Advantages of this memory design and management techniques. Hardware architecture has separate memory for data and instructions, as we already discussed. Both instructions and data can be fetched at the same time. It is also a very comfortable way to the users. This is basically used in modern CPU CAD system. Fetching instructions and data occurs simultaneously. And our 9th question is to elaborate the pipeline and parallel processing capabilities of the unit and hazard management technique. Pipeline. The instruction cycle consists of 4 queue cycles, namely Q1, Q2, Q3 and Q4. In this pipelining, a fetch cycle begins with the program counter increment in Q1. During execution cycle, the fetched instruction is latched into the instruction register in cycle Q1. Data memory is read during Q2, which involves operand reading, and written during Q4, that involves destination write. So the instruction is fetched in fetch 1 and then executed in execute 1. Similarly, in fetch 2, the information is fetched and then executed in execute 2. It happens in the same way for the 4. Parallel processing capabilities. It will run many threads, each is independent. Processor time is divided between threads. Threads or for sequence for many purposes can run at the same time. Threads can be easily added without affecting application performance. RAM variables, special timers can be shared or dedicated only to one thread. Threads can be prioritized. And then the technique involved in order to manage these hazards. A hazard occurs when 2 or more simultaneous instruction conflict. There are 3 types of hazards: data hazards, control hazards, and structural hazards. Data hazards arise when an instruction depends on the result of a previous instructions in the pipeline by the overlapping of instruction. Control hazards arise from the pipelining of branches and few instructions that makes the changes in PC. Structural hazards usually arise from resource conflicts. In few cases, hardware cannot support all possible combinations of instructions, which leads to overlapped execution. And now, in order to avoid these hazards, few methods can be followed. A stall or a bubble in the pipeline can control unit stops the instruction fetch mechanism and puts knobs into the pipeline. This makes a sensitive instruction to work alone. Register renaming can be done to prevent hazards. Renaming or renumbering can be done instead of having fixed number of registers. A branch delay is an instruction written in the assembly source code after the branch that is designed to execute whether the branch is taken or not. A knob should be inserted if there are no instructions that can be executed without a dependency on the branch. And our 10th question is to find whether processor level parallelism is available in the element selected and then illustrate its catch coherence and protocol used for handling memory hit or miss. Basically, there are several different forms of parallel computing: bit level parallelism, instruction level parallelism, data level parallelism, and task level parallelism. Cache coherence and protocol used for handling memory hit or miss. Snoopy bus protocol. Caches are used to reduce latency and to lower bus traffic. Cache coherency provides hardware to ensure that both cache and memory are consistent. Read miss, write hit, write miss, read hit are the methods that we followed during accessing of data from cache memory as well as in the data memory. Before update, this is the instructions. In order to write through the information from the cache memory, this is followed. The information of P2 is sent to X1 and then X1 is to the cache of X1. In order to get back the data from cache memory, write back method is used. The data from cache memory is sent to the data memory. Read hit is performed in local cache memory without using the Snoopy bus for invalidation or causing a transition of state. Block replacement. When a copy is in cache memory, it is to be written back to the main memory by block replacement method. However, no replacement will take place when the copy is either invalid or reserved or in invalid state. That's it. Now I would like to show the data sheet of my particular IC. This is the data sheet of PIC16F62X. Block diagrams, instruction set, all the details of timers are all present here. And then instruction set. This consists of several number of instructions. That's it. Thank you. And now I would like to discuss the difficulties that I faced. Firstly, searching for a proper microprocessing element such that the related data is present, and also checking if no one else is selected is really a bit time taking. And it took really long to complete a single block diagram in the starting, but later on I was able to do it pretty fast. And then the register organization part, I think fifth question. Register organization. Since there are many register organization, tabulating all them was also time taking. And hazard management techniques, I need to browse many websites since it is not available in the chosen data sheet. So gathering all the information from the website and understanding it took really long. And I need to mention that I learned a lot when working an assignment. It really took a long time, but it's really helpful. We gained a lot of information. Thank you.